Across partial differential equations, boundary conditions come in three main types, and today we will look at each one in turn. The first type is called a Dirichlet condition. A Dirichlet condition prescribes the value of the function directly along the boundary. For example, we might say u at x equals 0 and time t equals a fixed value, capital T naught, meaning the function itself is pinned down at that edge. The second type is called a Neumann condition. A Neumann condition prescribes the derivative of the function in the direction leaving the boundary. In symbols, we write curly du by curly dx at x equals 0 equals some prescribed value, meaning the slope, not the value, is fixed at that edge. The third type is called a Robin condition. A Robin condition mixes the two together. It is a weighted combination of the function value and its outward derivative. In symbols, we might write alpha times u plus beta times curly du by curly dx equals some constant at the boundary. Now let us connect these three conditions to a real physical example, the heat equation, describing temperature along a rod. The physical meaning of each condition follows directly from what it says about temperature at the ends of the rod. A Dirichlet condition on the heat equation means a prescribed temperature. In other words, you are physically holding one end of the rod at a fixed, known temperature for all time. A Neumann condition on the heat equation means a prescribed heat flux. The special case of zero flux means a perfectly insulated end, so no heat energy can pass in or out through that end of the rod. A Robin condition on the heat equation models convection. Here, heat leaves the rod proportionally to the temperature difference between the rod's end and the surrounding fluid, so a bigger temperature gap causes faster heat loss. Let us check our understanding using the insulated case. Suppose we apply a Neumann condition of 0 at both ends of the rod, so curly du by curly dx equals 0 at x equals 0 and also at x equals the length capital L. Since no heat can escape through either end, none of the rod's thermal energy leaves the system at all. So instead of cooling down to match the temperature of the outside world, the rod simply redistributes its own heat internally, settling toward a single, constant equilibrium temperature,